Right. So I am going to be starting vector calculus today. I was going to make a video for last week, Friday, but then kind of I had some technical difficulties just actually kind of recording it and stuff. And then in the end, I figured I could restructure some things to actually put it all into 3 weeks. So there's no video from last week. You guys could, you wrote your test, and hopefully at least everything up to linear algebra now should be kind of settled in your mind. You've had the lecture, you've written the test, everything's done. We're now going to do calculus and optimization. I think in the previous iterations of this course, I found the first week of continuous optimization was just very conceptual and very light on content, and usually we end up finishing like an hour. So what I've done is I've moved some content out of calculus into that week, so it's a little bit longer. And then I've just restructured calculus a little bit because I think the lecture sides of calculus were also quite jumpy. So it should all be to the service of clarity. And I think in the end, what it meant is that it's actually now going to go quicker. We'll see how it goes. We'll manage the course as we need to. The one flip side of this is that I'm only going to finish vector calculus next week, which, as you've noted, is there's a date that's been set for that. I respect the fact that when I give a course outline, I'm somewhat, beholden to you or responsible to you guys to try and adhere to that. So if anyone has a fundamental objection to moving the test next week, I will, then fine, we can carry on doing it, and I'll set your test appropriately based on the content we cover today. Your tutorial is up, and then, we'll just do a lot of consultations next week to make sure that everyone's comfy with the content for the test. The alternative is that we can push it by a week. I think I've heard from some people offline that that's preferred given the proposals going in, but also, I'm aware that there's some other stuff happening in that last week as well. So complicated times. I get that you guys have a lot going on. I certainly don't want to contribute more to that than I have to. But you do need to do 1 more hour of test, and I do want it to be calculus. So that then the only unseen thing going into your exam is the continuous optimization. And I think you'll realize that that section is a little bit more easy to predict and kind of easy to know where you're at. So give it some thought. But as it stands, the test next week will be moved 1 week later. Okay, so unless anyone fundamentally contradicts that. Okay, any questions? Yeah.
You expect the previous test to be
Yes. So fundamentally, I don't distinguish in this course between exams and tests in terms of anything but schedule. You know what I mean? So obviously it's a 3-hour assessment, not a 1-hour assessment. But what you'll notice is that 1 hour of testing in this course always counts 10% of the course. And the reason I do that is I find some people struggle with exams. There's a time management thing, obviously, to that, but also there's just a stress thing. And so I don't think it's super fair if now your exam counts double the mark per minute than a test. So it is going to be almost exactly the same as your tests. It's just 3 hours now. And there's obviously 2 of them. Yeah.
So exam, how do you split the content for 2 exams?
It's going to be exam 1 is linear algebra, analytical geometry, and decomposition. Exam 2 will be calculus optimization. Okay. Which is another reason why I do want to write this test. Cool. I'll be doing a lot of, consultations and stuff like that, building up to exams and hopefully for a test as well. But, we can play that by ear. There is still that 1 week as well. That's essentially kind of like a revision time or whatever that we have available to us. I don't like to use that for lectures, but if we need, we can then also spend that time going over a concept that's maybe uncomfortable or whatever, and it's up to you guys to maybe then drive that if you want, or you can have that week off and we you just study and get in touch with me on Discord. The last thing to mention is I know I have a bunch of open tickets on Discord. I checked before the test that none of them were for the test, but they're all kind of test 1 corrections, which is fine. I will get to those. If you are expecting a response from me, it's coming. You probably have nothing to worry about there. I'm not going to be complicated, more complicated than I need to about it. I just haven't had time to sit down and think about it. So we'll do that. I'll do them all at once, and it's likely that after you get your marks for test 2, your papers will get back to you next week as well. We can do those as well at the same time. But hopefully there's not too many queries on test 1 or test 2. Cool. We're good. As a whole, where are we at with this course? I know I have a sample bias here, you know, the 5 or 6 people plus people online, up to 10 people who actually come. But is this at least fulfilling the role that I said it would? You know, are you getting more intuition for the concepts? Is like things becoming clearer, or does it just feel like a, you know, rehash of second year and you can't wait for it to be over? I'm genuinely looking for feedback here so that I can at least improve on calculus if we need to. Yeah.
Well, for me at least, learning algebra in second year isn't very learning anything.
Yeah.
So this has cleared up quite a few things for me.
Alrighty. Anyone else? Is this at least going okay for you? Yep.
Yeah, like it's very clear understanding what bases are and change of bases and all that stuff. But then your algebra itself isn't abstract itself, like compared to like calculus.
Yeah.
So I feel that it is basic
I see. Okay.
compared to second.
All right. So you still feel like it was a bit too abstract?
But once you do the calculations, the theory makes sense, but the theory doesn't make sense without the calculations.
Yeah, I think that's fair. I think that's somewhat natural, but a good point. Cool. All right, then let's get started on calculus then. I will prepare and say that this is one of those lectures that a lot of it is going to be familiar to you, and you're obviously going to get a little bit frustrated with me here. It's definitions heavy. The last 3 or 4 slides on this is always a mission. It's just like how to do high dimensional derivatives. It's confusing. Every time I look at it, I have to like think about it. So we'll go slowly and maybe even like recap it next week. But I think the kind of one of the best things in this class is that we do automatic differentiation. So that's coming next week. And that's something that's like the foundation of how like PyTorch and JAX are coded. So next week we look at how automatic differentiation works, and there's like almost like a fun test and exam question that comes out of it. But for this week, we're just going to go over the like basic calculus and chain rule and all that stuff. So you can expect that. And then next week, I think, is where this section of this course kind of shines. All right. So in this class, the most common function we will consider is one that takes in multiple dimensional inputs and produces a scalar. So let's get this pen out. We're in RD and we're mapping onto R, okay? So in machine learning, that is obviously something like parameters of a neural network mapping onto a loss. And then you're trying to update your parameters such that you can do something clever to that loss. We will get to that when we do continuous optimization, but the fundamental aspect of any of that is you need a derivative, okay? So we're going to take a function f, which assigns for every input x. Note that it is bold, so denoting a vector in this case. So it takes for every input x and produces exactly one function value, which is f of x. Okay, typically in machine learning, we quantify the error as a function from RD to R, as I said, where the model parameters are usually RD, and how well we approximate the target value is in R. Okay, so that's just a scalar value. And you'll note that if you ever try to use like a PyTorch grad function or something on something that isn't R, you know, like it's an RD, it'll complain like that because it's somewhat ambiguous how you want it to combine those two things. Okay, and so actually we will most often be in a situation where f has data pattern input as well as a set of modeling parameters. In that sense, though, usually you consider your data set as static. So, you know, when you're writing out your loss as a function of just your parameters, so in this case, x is a parameter, not an input, you consider your data set static, right? And you're optimizing over that, which is one of the problems with things like online learning and changing data sets. It becomes tricky because now that is a moving target for you to optimize your parameters on. It's one of the fundamental reasons why RL is so extremely hard, because not only is it a moving data set based on your own interactions with the world, but now it also depends on your output of your at the previous time step. So it's temporally correlated and a changing data set. Okay, so then knowing the gradient of f with respect to one or more of the model parameters allows us to optimize them to reduce the error in our fit or prediction. Okay, and the easiest example of, I think, like these parameters is a Gaussian distribution, right? And how you parameterize these things is usually then how you pick a functional form. Okay, so you can Wi-Fi. Guys online, can you still hear me?
Yes, we can hear you.
Okay, great, thank you. All right, we're back. So as you can see, I've scribbled a Gaussian, and we have a mean and a covariance. Those are the parameters of your distribution, right? And those are called sufficient statistics. In other words, they're sufficient to explain every aspect of a Gaussian, right? They're not sufficient to do many other things, but for a Gaussian, those are sufficient. We don't cover the probability side of this course anymore, but that's just like a nice, I think, a useful definition of parameters to know, be it for any kind of model or a distribution itself. Now, what we usually do instead is say that, okay, it's really, really difficult to optimize that or pick what's going on there. So instead of that, I'm going to write that as a function of something else. Okay. And so then you end up saying that u is equal to f of x. Okay. And that's fundamentally what a linear regression is doing. It's saying for every point along this line, please predict what the mean is, what the average is. Okay. And so now you can change the mean of a Gaussian at every point in the space. And so it's going to give you a Gaussian at all those points in space. All right. So we can then make these arbitrarily kind of complicated by just changing the parameters. And in that sense, now mu, the parameter we really care about, which is the mean, becomes a function of another set of parameters, which can be much higher dimensional, meaning that we have much more flexibility to be able to set those parameters. Okay, so it's just almost like a change of variables from one difficult thing to estimate, which is mu given x, to something that is more easy to estimate, which is your theta values, which gives you a function for every x. One of the reasons that works is because then it can generalize. If I have to learn a mu for every x, then I have to see every x. If I learn a function that takes in x and produces a mu, now it can generalize by just seeing maybe a handful of data points. You know, I give you that one and that one and that one, and now you can interpolate between them, and hopefully you have a model that does well. So that is very much the idea that we're shifting to here, is we're taking the parameters of a distribution of something that we want, changing them into a model parameters. And to do that, we need to be able to take derivatives. Okay, and so here's the big old textbook map of derivatives. As you can see, partial derivatives, the Jacobian, the Hessian, and the Taylor series expansion is where we're going. A lot of these concepts should be at least familiar words, but we'll explain them and try to kind of link back at least a little bit to linear algebra for some of them, like the Jacobian. But to begin with, we have a difference quotient. Okay, and so this is the idea of a gradient coming out of like the basic, not basic, but like the notion that you would get at school, right? It's, I have some function f, and I want to know when I make a small change in the x in my input, how much of a corresponding change is there in y. Okay, it's rise over run, and that's going to give us the average. Okay, that's going to give us the average gradient as along the path that we, or across the distance that we jump in x. Okay, so here, this gradient there, let me change color so that it's discernible. The gradient there is actually somewhat less than the ultimate gradient we get, right? You can see that this is larger up top there. However, if we then move to this point here, the gradient is actually slightly larger than what the blue line would indicate, okay? And so we're in this case where along that line, we're actually incorrect at almost all points. And so what we end up with just though is the average gradient taken across this entire jump, okay? Which is fine. That's a reasonable thing to do. And that then gives us something that almost approximates the curve by that blue line. However, that's obviously not always going to be fantastic. And so the whole idea of the derivative is that instead of doing the difference quotient, what we're going to do is we're going to try and take this step to be infinitely small. Okay, so we send this little bit over there to be really, really small. So we're getting an extremely precise kind of representation of this gradient at like a tiny little point over there. In which case now the average over that little span is going to be a lot more consistent, and so you're going to get collapse onto the correct gradient. The downside is that now you have to once again be able to do this at all points along X. Okay, so that's essentially the difference quotient, and then how you go from that to the derivative. We'll see the derivative equation now in a second. So this is the definition here, and we're going to use the example of a polynomial and derive the actual power rule as the first example of this. I do like you guys to know how to do this derivation for the power rule. I think it's a useful one, but there's a few kind of niggly bits to it. So while we don't always derive a derivative from first principles, it's informative to do so for f of x equals x to the power of n. We can actually be even more rigorous, but this is sufficient for our purpose. So as you can see here, this is the same. Let's focus on this bit here. This is quite clearly the same equation we had on the previous slide, except for now, instead of delta x, we have h. So h is coming in there and there. This is irritating me today. X is coming in there and there. But fundamentally, it's still just, I'm taking a small step in my input space. How does that correspond to, how is that the, when I take that small step in my input space, how much does my output change compared to that small step on the input? All right, so again, rise over run. But as I said, the idea is that we now want to take that small step to be as small as possible. All right, so we're taking the limit of h to 0, so that now we get a very precise estimate of the actual derivative at that point. Okay, and so this is something to remember going forward, and it's a mistake that is easy to fall into. In a lot of cases, people use things like Taylor expansion as a method in other machine learning properties. There is, let's see if I can remember it now. There's a way of approximating a Gaussian distribution by using a Taylor expansion, the Laplace approximation. A lot of people will use the Laplace approximation and then treat it as if it's true. That's not valid because, again, your derivative is a local thing. It's actually only a good approximation around that point there. So can you imagine if I was trying to use the Taylor expansion, and we'll come to the Taylor expansion at the end of this lecture, but can you imagine if I was trying to use a method that was based on gradients and I was only taking the gradient here? It's not going to generalize very well when it's up there, right? Because that gradient up there is now a lot larger. So you always need to make sure that if you are doing gradient-based methods, that you are updating that derivative at all points where you move to, or that at least your approximations are stable. And this is a fundamentally kind of insightful point to machine learning, right? Because you're doing gradient descent, we try to act as if we're taking this really positive like step towards a minimum in this really complicated neural network space. And again, what we've done with an artificial neural network is we've taken the one thing you want to estimate, which is the mean at x, and replaced it with a function of 1 billion parameters. So we're now estimating 1 billion numbers, and we're now trying to optimize that. It's not going to always be a particularly useful step. It's an approximation based on a little bit of data, but because we do it so often, and we're constantly checking that gradient at every little step in this parameter space, it works. So when you're dealing with derivatives, especially in machine learning and especially in like these practical settings, a lot of small computations done very often is usually a lot better than something that is very kind of like one big computation that you try to extrapolate. Okay, And so things like Gaussian processes and stuff like that tend to work very well when they're interpolating, but then kind of extrapolate somewhat poorly. But machine learning also suffers from those problems as a result. Anyway, let's get back to just the definition of a derivative. So we're now going to take in our actual functional form and substitute it in for f of x. Sorry, I'm just going to close this and then do it on the other version. There we go. Okay, so we're now going to take in our functional form, substitute it in here. So the function we have is xn, and so I'm just going to say x plus h to the power of n. Okay, so that was the input to f was x plus h, so obviously it just fits in around those brackets there. And then f of x here, xn, and then h stays the same. All right. Now, I've drawn an example at the top there of what is essentially going on from this step to this step here. A little bit tricky, and it's one of those ones that I always have to look at anyway, or as well. Now, this is, so the last step is an application of the binomial formula. It's this case here. We have n choose I, and the form of this that I like the most is that. Okay, so the numerator here says how many different combinations of things do I have, right? Things being number of entities in my system. I don't care about ordering. All I care about is how I've split those things. And so I have to take into account factorial I, where I is the number of those things I'm sampling from my set. And so I have to take into account the fact that there is a number of orderings of the group that I pluck that I just don't care about. Those are equivalent to me. So I divide by that to indicate that I just don't care about those orderings. All I care about is what I sampled. Similarly, there's also n minus I combinations or kind of ways of sampling or leaving the other things behind. Okay, and I know I'm explaining this vaguely. We'll see it concrete now in a second. But that's the number of orderings of things that I left behind. And again, I don't care. All I care about is what are the two groups? What are the two different kind of ways of ordering these things? And so I divide by that. Okay, so it's effectively the number of samplings or the number of entities I have, and then divided by the arbitrary ordering within the two groups that I'm, plucking and not plucking. And then this is just the definition of factorial. So in factorial, you take every number from starting at 1 up to n, and you multiply them together. Okay, so 3 factorial, for example, 3 times 2 times 1 gives you 6. Okay, similarly, and I'm sorry if this is old hat to you guys, but let's just do it for completion. Similarly, if I have 0 factorial, that's equal to 1. That's a definition thing. Okay, that is also important in this proof. All right, so that's essentially what where this is coming from, is the fact that if I have something, a polynomial of this form, right? So x plus y raised to the power of 2. If I FOIL that out, I get x squared, 2xy, and y squared. The coefficient at the front here, the 2, the 1, corresponds to this equation here. Okay, that's saying, and you can see the summation starts at 0 and goes to n. So this is saying, if I have a certain combination of x's and h's, how many orderings do I have of them? All right, and in the case of starting with I is equal to 0, you're going to come in, you're going to substitute 0 and 0, and so you're left with x to the power of n, h to the power of 0, which is 1. There's only one ordering of x to the power of n, okay, and so that ends up popping out of that coefficient there. Right, and so for proof by concept, let's just add that in. N in this case is 2. Okay, so we have 2 factorial. I was 0, so that becomes 1. And then n minus 0 is still 2. So you end up with n factorial divided by n factorial gives you 1. Okay, life checks out on that front. And so that's kind of the rewrite that we're doing. The same thing happens then when we get to I is equal to n in this case. So when I is equal to n in the summation, at the end of the summation, you go n minus n, that's 0. So you get x to the power of 0 is 1, and you end up with h raised to the power of n. Once again, we can now come up top here, look at n factorial, that's just, for example, 2, but now I is equal to n, and so that gives you 0 factorial, and so once again, we collapse back onto n factorial over n factorial, which is 1. Okay, And so you end up with the coefficient of 1 out front there, 1 out front there, based on the kind of extremes of the summation. All right. But now what's interesting, at least in the simple case, and you can then kind of trust that it extrapolates if you want to. This interesting case is then when we're in the middle here of this coefficient, right? So what happens for I is equal to 1, all right? So in that case, n is 2, I is equal to 1. So we have we have 2 minus 1 is 1, and then I is equal to 1 is 1. So we're now in a case where we have xh, or above here it's xy, all right? So let's come and sub that into the binomial formula at the bottom. Again, n is 2, I is 1, 2 minus 1 is 1. So at the bottom now we have 2 factorial divided by 1 factorial times by 1 factorial. This just gives you 1 at the bottom. 2 factorial is equal to 2. And so you end up with your coefficient of 2 out top here. All right. So that is the rewrites that we're getting to try and just take into account these coefficients out front, the number of different ways we can structure x to the power of whatever or x times y. And so it turns out in the case of xy, there is 2 different orderings, xy, yx, and so you get your coefficient out front there. All right, then the rest of this is just the power. So essentially this here corresponds to the foiling of those brackets. You can remember that step. The reason we have to foil the brackets though is so that we end up now in a case where we can start considering the negative out front here and starting to simplify the addition of all these terms. Okay, so if we wanted to summarize our steps where we're at right now, you sub in your function, and then from here, FOIL the brackets. Okay. But now you can consider the kind of special case of the summation over here, which is when I set I is equal to 0, and you can see it kind of fall out over there. And when you set I is equal to 0, you get xn. All right, as we just saw up top here, x raised to the power of whatever n is. Okay. And so that's really, really nice because out here now flops essentially that becomes x to the power of n, x to the power of n plus the summation from I is equal to 1 up to n minus xn. Okay, and you can see then that those two things cancel. All right, and what we're left with then is a summation starting at 1 instead of starting at 0. All right, it's a little bit of a subtle-ish step, but hopefully it's making sense. And then we cancel those two terms. So now that minus xn on the right has vanished. All right, this is looking a lot cleaner already, but it's still not in the form that we really like. What we can notice in this case is that, well, we have hi and h over there. And because we now no longer have this kind of dangling subtraction term, we can just do this division directly. And so you get h minus 1. Okay, up in the top. The last thing we can do is we can now apply this trick that we did previously where we considered the first term of the summation. We can do that once more. Okay, and so now we're going to split the summation from I is equal to 1 to n. We're just going to split it into the term for I is equal to 1 plus the summation starting at 2 up to n. Okay, and that's exactly what we've got up front here. This corresponds to that bit there where I is equal to 1. And I'm starting to make a mess. We're all following so far? Okay, it's just literally pulling out summations after you FOIL the brackets. Okay, but what's really useful is that we note that when we have I is equal to 1, because we had that one division come into our numerator now, when I is equal to 1, we get back to h0, which is 1. Okay, super, super helpful when we want to then apply the limit of h going to 0. Okay, as you can see here, h going to 0, but h isn't in this term. And so you just drop it. That has no effect. However, this term has an h in it. And so when we apply that limit, it all goes to 0. And so this entire bit here falls away. And so what we're left with is just the term x raised to the power of n minus 1. And then this little bit here gives us your combinatorial kind of to calculate your coefficients. How many ways did we could we have ordered our variables and then collapse them into the sum? You know, x, y, y, x, whatever. Okay, and ultimately, when you substitute that in, you'll realize that this is now 1 factorial. All right, by definition, it was always going to be 1 there, and so we end up with n factorial divided by n minus 1 factorial. But n factorial is just n times n minus 1 factorial. Minus 1 factorial, right? If I said 3 factorial, that's just equal to 3 times 2 times 1, which is just equal to 3 times 2 factorial. All right, so we can regroup those terms. And in this case now, those cancel. And so we're just left with n out front. And that is the full, somewhat tedious derivation of the power rule. It is a particularly useful rule, probably the most common one you'll see. And kind of, I think it's a useful first example of these things. Is everyone comfortable with this? Any questions? Very good. Guys online, can you do this derivation?
Yes, sir.
Right. Thank you. All right, there are a bunch of these. And what I'll tell you is that the only one I expect you to know the derivation for from the quotients is, from the difference quotients, is this one, the power rule. You don't have to know how to derive product or sum or chain. But they all are all useful. Or the quotient rule for that matter. They are all useful. So for example, if you have the product of two functions, f of x times g of x, you're taking the derivative of all of that. So sometimes it helps if you Great. About that, everyone. Relatively unprofessional. Okay, so what often helps is if you rewrite these functions. I always find it easy to. There we go. I always find it easier to think of these functions as like one thing and rewrite the symbol. So if f of x is then x times g of x, then what you're doing is taking the derivative of h of x. All right, and then that's now the rule that you want to apply is that when I have to take the derivative of this, it's f of x, g of x plus f of x, g prime of x. Okay, this is a useful way of looking at it, especially when you come to doing the automatic differentiation stuff in the next few weeks. It looks pretty trivial, but when you have a really big function, it helps a bunch to always rewrite it that way. And that is, again, kind of the whole point of what we found with calculus on computers is representing things as small units and then redoing principles or redoing rules to the small units is highly effective. That is the foundational rule of automatic differentiation. So if it seems like I'm being slightly pedantic, it's because I also know where we're going with this. Right, but here's the rules. You're welcome to memorize them. You can derive them as well. Things like the quotient rule is actually just the product rule. Quotient rule is actually the product rule, just where the coefficient of g here is f of x, g of x inverse, right? And so when you apply the power rule to the g of x inverse, you end up with the g of x minus 2. Okay? Power rule being obviously this one we just did over here. Cool. Sum rule, if you are taking the derivative of a summation, that's the same as the summation of the derivative. That's really useful. If those of you who are tracking the concepts from linear algebra are like watching, you'll notice that what that means is that the derivative is a linear operator. Okay, you can distribute it. The sum of the operator is the same as the operator of the sum. And then finally, chain rule. Chain rule says that if I'm taking the output of one function and applying it as the input to another, then I can take the derivative of that entire system by applying this rule, which says first do the derivative of the outer function and pass in the input of the first function as if it's unchanged. Okay, obviously we want to just know how that function itself is acting on the system at the point where it's being applied. All right, and then lastly, how is the point it's being applied changing as well? Okay. And so this is how you denote a composition of functions. All right, so here's an example. Consider the function h of x, and that's equal to 2x plus 1 raised to the power of 4. Again, it helps if you always rewrite these things in that kind of notation and these reusable units. So what we're going to say is, well, it's a chain rule, so I have to be able to write my function like that. And now what is my g? What is my f? Okay, well, in this case, g is just being raising something to the power of 4. All right, so it's the output of f, whatever that may be, just raise it to the power of 4. And then obviously now f needs to just be saying the internal bit of those brackets, 2x plus 1. I hope that's not conceptually tough. I'm going to go quickly through this, but slow me down if it needed. And so you can get the derivatives of these things separately and then use the chain rule to combine them. Again, that is really, really powerful, because doing the quotient rule kind of way of, this derivation we did for the power rule, trying to do it on something like this or something even bigger is painful. Okay, so the fact that we can always then just break down the computation into small pieces where we have little rules that are always going to be valid for them, essentially these 4 little rules plus the 5th one being power rule. You have the 5 little rules that and then you just break down your computation to little reuses of these concepts. Okay, that's really, really powerful. Fundamentally, that's how transformers are currently being trained. Okay, and so now specifically in this case, what's the derivative of 2x plus 1? You just drop the x, it's 2. That is an application of the power rule. All right, so in this case we have x raised to the power of 1. So the power rule says that we take the n value, bring it down to the front, and then subtract 1 from that power. So running through this, we bring 1 down front, x 1 minus 1 is equal to x to the power of 0, which is 1. So that just falls away, and what we're left with is the 2. Okay, that's the power rule being used again. And then same thing here for the f. You bring down the power to the front, subtract 1 from it up there. Cool. And then now that we have that, you just take the product of these two things together. Okay, so we say f at x, what is that? That's just 2. And then g, the derivative of g to that function applied to the output of f, which is then just this over here, and then you can substitute in the output of f, which is 2x plus 1. All right, that just came from up there. All right, so with the original function. All right, chain rule, hopefully old hat to everyone in this room. But then obviously they extend into higher dimensions and you can kind of blow things up. What I will say is this where the one thing becomes tricky. So a lot of the rest of today's lecture is just going to be an application of this, these ideas. You kind of pull them up slowly in these slides. However, keep aware of whether or not you are differentiating functions or their inputs. So you can have multiple outputs to a function, you can have multiple inputs to a function, and you need to know how you differentiate this is whether or not your derivative matrix becomes rows or columns, or how many rows or columns there are. Okay, that's the one confusing aspect of this where I find people get it wrong. And it's one of those things where, like, I know you can do it, but in an exam it just goes awry unless you've actually thought about it a bit. So keep your wits about you when you're doing that. So we can have the generalization of the derivative to functions of several variables, and this is known as the gradient, which we will need partial differentiation to obtain. So partial derivatives then says that if we have a function of high dimensional inputs, so note that up to now we were just talking about a single variable input x, right? So now we generalize into essentially what we said was our initial motivation, having high dimensional inputs. Okay, still mapping onto a scalar for the moment. The components of x are represented as x1 to xn, and we can define the partial derivative as follows. So again, this is now a vector being passed into a function. Okay, you can essentially apply the exact same rule we had from the previous slides, where all we're doing now is applying a small change to one of those input parameters at a time. One of the dimensions of your vector space is being perturbed at a time, and then you just track the rise over run of the function, kind of at just in terms of that direction in isolation, dimension in isolation. So you can see here when we want the partial derivative of the function just with respect to x1, then we just take that small step in the x1 case only, and x2 up to xn are kept the same. All right, everything else is normal. If we want to then take the partial derivative with respect to the input variable, then you just apply the plus h at that little perturbation away, that little approximation of the rise over run. You apply that just to the xnth variable. Okay. Importantly, you can collect this into a row vector called the gradient or the grad, denoted by this upside down triangle, which says, give me all of the partial derivatives of f with respect to x. Okay, all of the xi variables. This becomes a 1 by n vector. It is a row vector. I will give you a geometric interpretation of this next week. It's the first thing we'll start with. But it's essentially, if you remember when we were talking about linear algebra, we were talking about the fact that row vectors and column vectors are fundamentally different things geometrically. All right, column vectors are vectors. Row vectors are called covectors, and they gave us a way of measuring distance. What you'll find is that this derivative is essentially a way of measuring distance, but by elevation. Okay. I'll show you a visual example of that next week. It looks like a map. Yeah.
Is that plus h of x1 wrong? Is that supposed to be there?
This.
Yeah.
Yeah, that's wrong. It's a good catch. Let's just delete that. Yeah, nice catch. Thank you. All right. Fortunately, all the same rules apply because, again, we're just perturbing one of the variables at a time. So if I want to take the partial derivative of this function at the top with respect to x, then first you do the outer function, which is to just say, you know, f of x, y is a function of just dots raised to the power. And then after that, we now have, and that's what notation do we want to do for that? Let's just say h of g of xy. Okay, and so now in this case you have h of g as your first variable, and that's raised to the power, so that's just g squared. Okay, and you can come along and do the same kind of product rule off the top of that. Sorry, not product rule, chain rule off the top of that. Okay, and so this example here, we drop down the 2 to the front, that becomes there. You're applying the power rule, so you subtract 1 from the power up at the top, so that becomes 1, and then you keep the function the same again. All right, so once again, there's glob here, what I wrote as g, just kind of gets substituted back in, and then after that, you come and take the same partial derivative you were applying to the first bit, you apply it to the internal bit. Okay, and so now it's exactly the case we were looking at over here, except now it's obviously x and y, so x1 and x2. But you're only going to consider how x changes over in this function. And so any variable that isn't x is treated as a constant. It's fixed. You can see it here, especially without the typo. You can see x2 doesn't change, xn doesn't change when I'm only considering x1. In other words, I treat that as if it is some constant value of like 2. And we know that the derivative of a constant gets set to 0. Okay? And so I come along, I do the partial derivative over here. The derivative of x, we know that that's 1. And then the derivative of a constant we know is 0. So this just all collapses to be 1. Okay? And our answer is just that term out front over there. Then slow me down if I'm going too quick, but yeah, I don't want to be too tedious. Same story, we can do the same thing for y. So in this case, we just still drop the power down. That internal function is the only one with respect to x and y. So the beginning looks the same. But now we come along and we only differentiate this function with respect to y. So now x is treated as the constant. So that becomes 0. But now we're applying the power rule to 2y to the power of 3. And so we bring the 3 down front, gives you a 6. And then you have y, 3 minus 1 is 2. Okay? And then we substitute that all in and simplify our terms. And you can then just get the answer. Okay? That's partial differentiation. And then the important thing, once again, is how we package it together. It becomes a row vector. So it's that function with the partial derivative being all of our columns of that row. Okay? So we can once again generalize what we saw in one dimension to higher dimensions. You have the product rule, the sum rule, and the chain rule all being applied in the same fashion you would expect. First, you differentiate for the product rule. First, you differentiate the first term with respect to what you're differentiating to that bit, and you keep g of x the same. And then you come and add in. After that, you do the summation, where you now keep the first function fixed and differentiate the second. Okay, that's the product rule. Sum rule, the derivative of summation is the same as the summation of the derivatives. Okay, again, derivative is a linear operator. And then lastly, we can get the chain rule where we're applying the derivative with respect to x, where x is the internal like input to some other function g, and then f, we just looked at an example of that now, where we differentiate f with respect to g first, and then g with respect to all of our different inputs after that. Okay. Note that this bit here then is where you get the grad. This will come out as a constant times by the grad of g with respect to all of your x's. And so you still end up with the appropriate shape. Cool. Everyone happy for now? Right, nothing too complicated, tricky. Guys online, are we happy?
Yes, sir.
Cool. Let's take a 15-minute break then, kind of refresh ourselves a bit, and then we'll pick up with vector valued functions where now the output is in high dimensions. I'll see you guys in 15 minutes. Righty, guys, online, can you hear me?
Yes, sir.
Right, thank you. Before we start. Cool. Okay, so obviously we know that there are a there is a more general version of functions, namely ones going from high dimensional inputs to other high dimensional inputs. We've been focusing on one in particular throughout this course, which is linear mappings, but there are a lot of general cases of this. And so given a vector x, which is an n-dimensional vector space, the corresponding vector of function values is given by applying m different functional forms or independent functions, each to those inputs. Okay, and then in that respect, we then collapse back onto the examples we were just looking at, where we had one function acting on high dimensions. So once again, it's just this idea of calculus is fundamentally just the repetition of these small computations, or at least high-dimensional calculus, is the rules of one-dimensional calculus just being repeatedly applied into high dimensions for all possible output dimensions on all possible input dimensions. Okay, and so in this case, you can use the rules of partial differentiation from earlier for each of the independent functions fi. Okay. And then in this case, the partial derivative of a vector valued function going from dimension n to m with respect to xi is given as the following vector. So again, you've seen the notation for a partial derivative. It's just that value for the partial derivative being applied, but again, it's your first row now is always the f1, okay? And then it goes down to m rows, right? So when we're looking earlier, the number of variables determine the number of columns you get in this derivative. Now, the number of output functions, output dimensions of your function give you the number of rows that you're working on, okay? And because now this is the partial derivative with respect to all the different inputs, it's now going to scale over that way. And so ultimately what you end up with is getting this matrix you're now in a good position to define the gradient of a vector value function, specifically the following. And so we now end up with this matrix where the row is always the same function, where the columns are now increasing the input variables. And then if you look down the rows, you go from the first function to the nth function. And so your matrix here ends up being an m by n. Okay, this is the matrix that is known as the Jacobian. It still shares the same notation as the grad. It's just now kind of implied based on how the dimensions of your output. Okay, this Jacobian is really, really important. And we'll show a new example now where it actually kind of falls into a linear algebra. So there's a lot of ideas around if you're going to be doing a lot of work at the intersection of linear algebra and calculus. For example, in something like differential geometry, the Jacobian becomes your workhorse in this case. Hessian, which is another matrix we'll talk about, of second derivatives to a lesser extent. Although Hessian is very interpretable. But this is your Jacobian, and the important thing, and we'll come to a general example of this now, but the important thing is to always remember that it is the number of output dimensions by the number of input dimensions. Okay, that's your Jacobian. And in that case, then it's just all these little one-dimensional derivatives, right? You just say, how does my first function respond when I change x1 a little bit? How does my first function change when I change xn a little bit? And you just do these little derivatives over and over and over, dropping them into their correct place in the matrix. Okay. Once again, you can apply the chain rule to these ideas. So let f be a mapping from r squared to r, and it's a function of x1 and x2, where both are functions of another variable t. Okay. Then what is the gradient with respect to t? So I've told you that f is a function of x, which is great. But x is a function of t. So for example, t might be time. All right. Now, if I have two variables that are changing over time, both of them affect a final variable f. I really want to know how my f is changing over time. F can be my bank balance. X1 can be school fees. X2 can be my salary. Time, t is time. All right. How over time am I kind of gaining wealth, let's say? And you can start to phrase systems very naturally in terms of these variables. But the good thing is that it's just chain rule, okay? I don't have to know exactly how my bank account changes with respect to time. All I have to do is know how my bank account changes when my school fees go up, when school fees change, or when my income changes, okay? Similarly, I can then separately consider how does my, what's the rate that school fees are going up over time, and what is the rate that my salary is going up over time. Those are two independent systems that you've now essentially decoupled. Okay, we love decoupled things. We've seen one example of this, which is the eigen and the singular value decomposition. All right, we like dealing in one dimensions. We like dealing in small little units of problems and then combining them later. Okay, and then same idea here. You can now treat f with respect to x and x with respect to t separately, and then just do the chain rule to combine the system into a single unified answer, which in this case turns out to be really easy. But you will notice the important thing here is that you have to get these dimensions right. Okay, remember, when f is a unit function, or a unitary function as one output, then you're going to have one row. Okay, so 1 by number of inputs, in this case 2. Okay, so your matrix here is a 1 by 2 over there. Similarly, now when I move on to a multivariate output with respect to one input variable, my matrix is now a 2 by 1. And only in this case do those matrices make sense. Okay, only now can you do a matrix multiplication of this form. And so you get out to, quote, a matrix of 1 by 1. Okay. And this continues, scaling up and scaling up. So for example, f can now be a function of x1 and x2, but now there are two different t variables acting on x1 and x2. Can you find the derivative of f with respect to the two input dimensions? And the answer is, of course you can. So in this case now, once again, f, it's a single output. You get a row. With respect to two inputs, you get two columns. And then now your second function is x1 and x2, which are functions of t1 and t2. So you get a 2 by 2 over here. Okay. And this is the kind of interesting thing, or the nice thing about the matrix multiplication is it's essentially a summation. Okay. We've seen that we've always written matrix multiplication as the following form. Aij xj gives you what? Let's not use that. Let's go yi. Okay. You have a summation over there. Right. The summation is over j, obviously. 0 to n. Okay, that is how you write matrix vector multiplication in terms of the summation rule. And so that summation, because it's in there, ultimately what it's doing when you take the product of a Jacobian, it's now adding up all the small changes in your system. Okay, it's saying, well, T2 must have changed and T1 must have changed. So now that's actually going to have an effect, or both of them are going to have an effect on X1. And so now when I want to consider how f changes with respect to x1, that product is going to multiply out both. Okay, and so you have all of your effects on the system being added together by this just really elegant matrix multiplication through the sum. Okay, is that clear to everyone? We're happy? Cool. And as always, it gets bigger and bigger. But so let f of x be this linear mapping, so a times x. So it's exactly what I just showed you now. In fact, you can see the equation at the bottom. The equation at the bottom here that I just wrote out for matrix vector multiplication. So f of x is equal to this matrix A, which is an n by n matrix multiplied by x. Then if we wanted to differentiate that system with respect to x, you take all of the little output dimensions of f. So again, f1 along the top, and differentiate with respect to all the input variables x1 to xn over there. Okay, excuse the errors in the subscripts there. And then lastly, now the output dimensions of fr go up to m, and so you then, every row is now an output dimension of f that you differentiate with respect to all the n variables. And so you can derive this fact, and we derive it at the bottom here. So give it a second. But you derive the fact that what gets left behind is just actually all the elements of A in their appropriate positions that they started in. And so the ultimate thing is you end up back with the matrix A, which works really, really well, because you'll notice that we just said, what's the derivative of, with respect to x of AX? Now, if we were in where that's obviously a vector. Now, if we were in a 1D system where we were dealing with instead A times X, and I was doing the derivative of a one-dimensional X, you would get A. Okay, that's intuitive. So it looks like in this case, what we come to is the fact that even in high dimensions, our rules look the same. You'll see an example now where it's actually not entirely the same, and it can get really tricky. But that's at least a nice sanity check that when we had a linear mapping like A, and we differentiate with respect to the input to that function, you just end up with the function. Okay, And so the way you would calculate this, and again, when we do these examples, I'll show you another example later on that's more close to what you're going to be doing in a test. But when you do these, you want to write the function out in terms of its summation. Okay. The reason for that is so that you can then differentiate with respect to the appropriate indices. Okay. So I've written out the matrix multiplication here, A as x, A of x, in terms of the indices. All right. This will give you, this bit here gives you the function fi. Okay. That is the output of that mapping in the ith coordinate. Okay. We're now going to differentiate that with respect to xj. Okay. And all we're doing here is then filling in those indices, right? We know that I have to come up here and say, well, the column I'm in is for fi. So that's dictated by that. And then the row I'm in is dictated by fi. And then the column I'm in is dependent on the j there. So here we have fi over x j. Okay. Partial derivative. Okay, and we're just going to fill in all of those little combinations into our matrix. All of the output dimensions, essentially, get differentiated with respect to all of the inputs. And so you'll notice here, and this is the one tricky thing about doing these derivatives with respect to like matrix multiplication and stuff, is because this summation is only valid at a single point. Okay, what this is doing is saying ai1 x1 plus ai2 x2 plus ai3 x3. I am then coming along and saying, well, what's the derivative with respect to only one of those terms? Okay, be it, let's do it in red. I'm going to now differentiate this entire thing with respect to one of the terms. So let's say derivative of x2. Okay, what is the derivative? What is the derivative of this with respect to x2? Zero, correct. Why? Someone else? Guys online, you're welcome to speed this up and give me the answer as well. Yeah, what's up?
Is it because x1 is in soup?
Exactly, because we're doing the partial derivative with the x2, so x1 is now a constant. That gives you 0. You then come and do the partial derivative of x2 with respect to this term. What's the answer? 0. Why? x3 is now treated as a constant. The only element in this partial derivative that is not treated as a constant is this one. And what is left when I do this derivative? Sorry, the notation's getting a bit messy. What is left when I do that derivative? Correct. ai2. We're left with aij, all right? So I substituted in 2 for j. That is the fundamental idea you have to keep in mind when doing these derivatives, is almost all of these elements of this summation are going to go to 0, except for the case where the aij, those two j's, match. You can see the summation is over j. You can see that the xi is over another j. Only where that xi matches will you have a remaining a term. All of the others go to 0, which is why you then recover essentially just that a at that item, that index. Okay? Scoff at this now, but towards the end of the lecture, this is going to suck. All right? We're going to have a break right before it, just so that I can read over it a second time. It gets really, really confusing. Okay? For a second time today. It gets really, really confusing. So keep your wits about you, and that's the whole point, is you have to keep those indices in mind. Make sure you're always matching, and make sure that you're always remembering to zero out most of that summation, except where those indices match. Okay, so that's now kind of ramping up to being bigger and bigger matrix multiplications and kind of derivatives of these big linear algebra functions. Okay, we can look at a few more examples. So there is obviously the chain rule now. So consider a function h which maps a scalar to another scalar. All right, but it is the composition of two other functions, f and g. Now, f takes in a two-dimensional input, maps it to a scalar. G takes a scalar and maps it to a two-dimensional output. And so, for example, f can be this case here. We're going to take in x1 and x2, the 2D input. We square x2, and then we take the product and we raise it to the power of the exponential. G, on the other hand, takes in this variable t, but uses it multiple times. And so it says t cos t, t sin t. Takes in one variable, produces two outputs from it. Okay? Now, G gets fed into f. And so ultimately what we have is f of G of t. Okay? Now we want to find, and that is called h of t. All right? Now we want to find what's the derivative of h with respect to t. Okay? And again, if you were going to do this the long way, you could try. You could take these elements here, substitute them all in, and try to do the derivative directly. And so you would end up with h is equal to the exponential of t cos t t squared sine squared t. And then you could try to differentiate this directly, and it would suck. And you would end up doing probably like the product rule or the chain rule implicitly anyway. Or you can just remember the chain rule, write it out like this, and make your life really easy and say, well, I'm going to treat each of those little pieces separately. Okay? And instead of differentiating h with respect to t, I'm just going to first do h with respect to x. Input to f, yeah, x. And then I'll differentiate x with respect to t. Let's do exactly that. So we come through here, what is f with respect to x? Okay, and you just do those derivatives. Ultimately, the rule for exponential is that e to the power of x is equal to x ex. Okay, so we're applying that rule there. Sorry, that was meant to be derivative out front. So that's the rule that we're applying over here. That's the power rule for exponentials. And then similarly here, we can do the chain rule on the second element. All right, because it's a little bit more complicated now. You then have to come through and say, well, first you have to, I think is this a typo? Am I reading this wrong? Then it's meant to be squared there. Anyway, someone can check me on that just now. I'll think about it during the break. Anyway, you come and you apply the derivative of f with respect to x2. And then similarly now we go and do the derivative of g with respect to t in all of those cases. Okay? That is the product rule in this case. So for example, if we're taking the derivative with respect to t of t cos t, then we first differentiate with respect to the first t variable. So that's d over dt t, and then we leave the second term as is, plus we leave the first term as is, and then do the derivative of the second. Okay, so that's why you're getting something like a summation out front there. The derivative of t in this case becomes 1, so you're just left with cos t, like that. Okay, and then secondly, now the derivative of cos t is then minus sine of t, so you get the minus sine of t out front there. Okay, as far as logistics of this course go, I expect you to know the derivative of the exponential, cos and sine, and then obviously all those other rules. But I generally don't ask you, I'm not going to ask you anything more than exponential log. Log is always going to be the natural log unless I give you a different base, but it's always going to be the natural log as well. Okay, so you need to know exponential, natural log, cos, sine, and then the other rules. Those are the only ones you need to know for this course. Don't go memorize things. Okay, and then the whole point now is that, well, we have the 1×2 matrix over there and the 2×1 matrix. And so when I want to get the final answer of how does the change in this one-dimensional element t affect my h, I just do the product. And because of the matrix multiplication, I sum up all of the effects that I care about, and I end up with a single term out front here. So end up with a single term out front here that would have been really, really hard to do directly, but actually just through the matrix multiplication is not that difficult. Okay, so that's the reason we really, really care about, at least the chain rule, especially in high dimensions, is it makes computation much easier. Okay, And then here is just the summary of how you get your dimensions where for input or output functions. So for example, if you have scalar inputs, scalar output, you get a single output vector or a single output element. You have high dimensional inputs, scalar output, you're going to get a row vector. If you have scalar inputs, high dimensional outputs, you're going to get a column vector. And then obviously if you have high dimensional inputs, high dimensional outputs, you get a matrix where the shape is m by n, where m is the dimension of your output, n is the dimension of your input. Okay. Everyone comfy for now? All right.
Sorry, did you say that M is the output?
Yes.
Okay.
Yeah, the number of rows is the dimension of your output space. And this has a pretty neat, at least up to a point, interpretation for us, particularly because we can relate this to our change of bases example from linear algebra. All right, so can we determine how much scaling a change of basis causes? So consider you have the two sets of vectors, B1 and B2 as your first basis and C1 and C2 as another basis. If there is a mapping that will convert B1 to C1 and B2 to C2, how much does it scale the space is a question you might be asking. Now, again, I know you guys all understand determinants and things like that, but let's run through this and see how it relates to what we're doing now with the derivative. So approach one is just the fact that we actually do our change of basis calculation from last time, right? You know how to do that. You said that, how do I write my new basis vectors in terms of my old? That gets my forward transform. That forward transform is then J. Okay. In this case, it was really, really easy because this is the canonical basis, but I have been informed that you guys can do this calculation anyway. And it's a really important one for this class, obviously. Now, we then also know that since that is our change of basis, and we want to understand how it stretches the space, again, how much volume does it add or area does it add? In this case, it's 2D, so area. You just take the determinant. Okay, so that's 3. We understand that. We understand the determinant of our forward transform just gives us the stretch of the space when changing basis. However, there is another approach here where we can write out f of x as a function of our inputs. Okay, now, fundamentally, I know that if you look at this for like 30 seconds longer, you'll all catch me and say, well, actually, what is this? This is just a mapping J of X, right? So I understand that given this example we just did from here, the answer kind of falls out. You know what I'm saying? When we took the derivative of, with respect to X here, of F, it was the derivative A of X, which gave you A. But that's kind of the whole point of what this example is trying to show you, is that I can extract from a function the matrix that represents that function. Okay? And so that's now the point of where we're going with this example. So I have my function over here. Let's assume that that's what we've been given. So what I'm going to do is I'm going to take the derivative of f with respect to all my x's. And so we can represent the derivative. They use the notation y1 and y2 for this case. So it essentially gives you a vector y1, y2. And so, as you would expect, I'm going to take the derivative of all of my output functions, all the y's, with respect to all my input variables, my x's, and you get your Jacobian. Okay? You'll notice that in this case, that is the exact same matrix as the change of basis linear mapping that we would have come to. So what is the fundamental thing that is the takeaway here? What do we, what's the message? And the message here is that your derivative of f gives you the closest thing to a linear approximation of f. In this case, it was a linear mapping, right? It was literally this j times x, and you can check me that that was, like that's kind of obvious given the f of x here. But that's important because what this means is that this is a way to connect what we're doing here in multivariable calculus, where it looks somewhat disconnected. How does it connect to linear algebra? It connects to linear algebra through the Jacobian. Your Jacobian recovers the closest linear mapping for a function. It won't always be exact, okay? In this case, we could have done something like this. And let's say minus 2x1 plus x2 squared. That's not gonna, that Jacobian exists. That Jacobian is not gonna be exact. It's not gonna be correct. Why? That's not a linear mapping. That F1 is not linear. And so now you get the closest linear approximation at the point that you evaluate x1 and x2. Okay. And that is the connection then between, at least I think that's the remarkable connection between linear algebra and calculus. Calculus is defined on a far greater set of functions than linear algebra. However, the Jacobian gives you that link. It gives you the closest connection you can make to a linear vector space in a linear operator for a given kind of high dimensional function. This comes up in a huge way in machine learning in a thing called the neural tangent kernel. And essentially what they do is they take a neural network, call it f of x, highly nonlinear, highly complicated, and they just do the Taylor expansion of the output of it. Turns out that in certain settings, that is almost exactly the same as a neural network. But you now have a Taylor expansion and you have far fewer parameters, and you can actually do some very clever things with the neural tangent kernel. For example, you can do the eigen decomposition of that Jacobian. In that case, now I can tell you exactly what that neural network is doing under certain assumptions. The assumptions usually have to do with the fact that x isn't changing very much, right? Because again, derivatives of local elements. Okay, my approximation, this linear approximation, is only valid in a small area in space. The same way that, excuse me, the same way that if I had a function here, the derivative here is obviously very different to the derivative over there. Okay, so I can only have this local approximation of it. However, under some very stable settings, if I assume that I'm actually only ever going to collect data from that bit there, now it's valid. Now that line looks really good. Now I don't need my neural network. Now I can just do the linear approximation of it. Cool. All right, so I get excited by that. I think it's cool. I think it's nice that the Jacobian is a linear mapping that approximates f. So the Jacobian represents the coordinate transformation we are looking for. It is exact if the coordinate transformation is linear. Again, that f of x was linear. If the coordinate transformation is nonlinear, the Jacobian approximates this nonlinear transformation locally with a linear one. Big takeaway. All right. Let's take a break. I'll come back at 4. We're coming up on that bit now where we're going to be looking at a lot of like intricate indices and stuff. And so come back fresh just to keep your wits about you on that. And then we have 10 slides left, and then we're done for today. I'll see you guys in a bit. I wanted to ask, how was everything okay with the recording of that one lecture? It was fun. There's no like background noise. Okay. Cool. Guys online, can you can you guys hear me?
Yes, we can hear.
Cool. Right. Let me share the screen. All right, let's wrap up today. So last half hour of today. Also, I just want to correct this quickly. So the derivative of this exponential to the power of ax is equal to ax. So you drop the constant. So in this case, this was fine because when I do the partial derivative with respect to when I do the partial derivative of this with respect to x1, the constant up front is x2 squared, which is why that falls out there. And then when I do the partial derivative of this with respect to x2, the constant is x1, that flops out there. And then you have the chain rule now because you have a square up top there. And so then you do the derivative with respect to x2 of x2 squared. And so that's why those two terms are sitting there. So that second one is first the derivative of the exponential, then the chain rule to get the square. And then everything makes sense. So yeah, sorry about that earlier. Okay, so in machine learning, we encounter situations where we need to take gradients of matrices with respect to vectors or even other matrices, which results in multidimensional things called tensors. So a tensor is to a matrix what a vector is to a matrix. Yeah, tensor is to a matrix what a vector is to a matrix. So anyway, essentially when you stack vectors, you get a matrix. When you stack matrices, you get a tensor. Okay, they are essentially these multidimensional arrays that you would kind of construct in Python, except for the fact that they're very hard to imagine in anything higher than 3 dimensions. So this is a third order tensor. It has depth, it has width, and it has height. Anything higher than that obviously becomes difficult. For example, so we have gradients of matrix valued functions with respect to other matrix value with other matrices. So for example, if we have a function f, it's going to produce a matrix and it also admits another matrix B. So then how do we take the derivative of this concept of this construct? For that. The general rule here, again, this is something that can kind of go wrong at some point, is that the dimension of the derivative is always going to be the shape of the output times by the shape of the input. So for example, if you're taking in a P by Q matrix B and that produces a function f which is shape m by n. When I take the derivative of f with respect to b, it's going to be the shape of f, m by n, by the shape of n. I will take every element of the output and take the derivative with respect to every element of the input. Okay, but it is always in that order. And the way you start doing these problems when you need to do a matrix by matrix derivative like this is you start by defining the shape. Okay, you start by saying, what shape am I expecting? This helps you a lot because it also ends up showing you how many indices you expect on the output. In this case, you just expect your Jacobian to have 4 indices, right? I, J, K, L, which corresponds to all of the 4 dimensions that you are going to produce. Okay, and then you know that then it's IJ at the top, KL at the bottom. Okay, you know that that's then how you're going to structure your indices, which becomes really, really important when you come down to the bottom here, and I'll scroll back up. You come down to the bottom here and you have to start pairing off the indices. Okay, the first thing to do is always start by trying to understand what the indices of your different matrices are. All right, one thing you can do to this is you can flatten out your matrices and you get them back to vectors. Okay, so since matrices represent linear mappings, we can exploit the fact that there is a vector space isomorphism, so a linear invertible mapping, between the spaces of Rm by n and the spaces Rm times n. Okay, so in this case, this is a vector of dimension m times n. So if m was 2, n was 3, you now have a 6-dimensional vector. Okay, here it's a 2 by 3 matrix. So you can always then just unroll this matrix into a vector, and there's a diagram of it now on the next slide, and then do your computation in this way. The only issue with this is that this unrolling thing is actually quite inefficient on a computer. It requires a lot of at least pointer arithmetic, but in general, it can just be really, really slow and frustrating. So we try and avoid these sorts of things. But if we consider our earlier example as an m by n matrix, then the valued function with the p by q matrix input, we can then reshape to rather work with the mn vector, so the output vector now in the kind of higher dimensional space, with a pq input vector. So you also unroll the input. Excuse me. So for example, here we have an A matrix times by and the x vector over there. Okay, A is a 4 by 2 and x is in R3. We want to take the derivative of all of the A's with respect to the x's, and excuse the change of notation here. A is now the output. It's not the matrix multiplication. So all elements of A are now going to be differentiated with respect to x. And the way you could do this is essentially you take this square here and you differentiate with respect to x1. And that's what this first block is. Then you come and you do it again for x2 and again for x3. Okay. And so now you end up with these rectangles that are the same size as your original A, 4 by 2, but now you have depth to it because you've done that 3 times, one for every x dimension. Now you have depth, so you just stack them together and you get that 3rd dimension at the bottom there. And again, we always know that the size of the output of this derivative is the dimensions of your output times by the dimensions of your input. In this case, dimension is just R3. Okay, does that make sense? You could, however, first flatten these things. And so you take this column of A and you put it under, you take the second column of A and you put it under the first column of A. Now you have a vector. And we're back to the regime that we were looking at earlier, where we had vector input, vector output, and it's a little bit easier to at least understand these things. So now, instead of getting a depth of 3, we just get 3 columns, one for every element of x that we differentiate with respect to. But it's the same fundamental idea of I have this column here, and I just do that derivative 3 times over, which is a little bit easier to understand. And then after that, now you just need to remember how to unroll it. Essentially, you take this bit up and you fold it back over, and then you can rotate it just to look the right way. Okay. Fortunately, a lot of the times when you do reshaping in NumPy, it automatically does it this way, but you always have to be careful. You always have to be sure that you know where each of these indices are now sitting based on how you unrolled it the first time. Okay. But it is good news that this exists if you prefer to do it this way. If you want to unroll your matrix, get a vector and then do the differentiation with respect to that vector. All right. That's a side point. So it's not something I don't prefer it that way, and I don't think it's super helpful. If anything, the way you do these derivatives stays the same. You're going to write it out as the function that we saw earlier, where you get the summation notation. Okay, so consider the following. So f is equal to a times x. F is once again m dimensional. A is m by n. X is n dimensional. So that's a linear mapping once again. But now you want to find the derivative with respect to a. So remember our earlier example, we did derivative of f with respect to x. We got a. We're now going to do the opposite to that. We're now going to differentiate with respect to a instead of x. Okay. So without looking down there, do you guys want to tell me what the size of this derivative is going to be? So what's the rule? We're going to hop on this one, man. So you can give it for a sec. Give it a sec. I'm going to say it because every exam, I get like at least 30% of people not doing this correctly. So what is the rule of the derivative? If I have an output dimension of m by n and an input dimension of p by q, the derivative is what size? Is this just not making sense? Or like, so why is this? Tell me why this is hard and I'll explain in a different way. Do you want to try? Okay, but give it a chance in the lecture. I mean, like the rule is that it's the output dimension by the input dimension. I've told you what the dimensions are. Okay. So in this case, there's your setting. Output is m, input is m by n. What's the dimension of the derivative of the Jacobian? iPad's even trying to give you a hint. Output dimension is m, input is m by n. What is the size of the Jacobian? And the rule is that the dimension is the output by the input. Yeah.
Is it fair to say it's m by n by m?
It's n by m, so it's m by n. Output of size of the output by the size of the input. I think that is what you meant, but
Is it by m by n?
did you kind of like mean to though? Like, did you imagine it as the transpose, or did you just kind of like, you know, say the industry, like the letters are obviously weird?
I think I mean it.
Okay. So again, is there I can only help if I know why that's not making sense. In this fundamental sense here, what you're doing is you're taking every element of f, and there are m of them. You're taking the derivative with respect to all of the elements of a, and there are m by n of them. And so you get m by n elements. Now, if we had the same setting here, f is an element of m, but now I was taking the derivative with respect to x. Okay, so this one here, input is n dimensions. What's the output? What's the Jacobian's dimensions? We did that example as well. So this system, f is equal to a times x. F is m-dimensional output. X is n-dimensional input. What is the derivative? What is the shape of the derivative of f with respect to x?
Is it not like the shape of the matrix in my hand?
Correct. There we go. So that is the first step to always solving these questions, is to try and think about, yes?
Can I confirm for this one?
Yeah.
I understand what it means to take a derivative because this means like how does it change with respect to changing?
Yes.
But the way I think of the matrix is saying it's like lots of numbers.
Yes.
So what does it mean to take a derivative?
With respect to matrix, well, then what you do is you just go into that matrix and you take the derivative with respect to all the little numbers in that matrix. So, consider it again. We had that example earlier where it was f was a function of x1 and x2, and then x1 was a function of time and x2 was a function of time. Okay. So in that sense, now we had a one-dimensional function. We had this function x, which is essentially taking in time and producing something in R2, x1 and x2. We were then feeding that into f, which was producing something in R, right? So now you would represent this as a vector, right? There were two arguments of the function, but there's also one vector in the function. Obviously, you would have to transpose it to be a vector. But you get what I'm saying? You're passing in multiple variables into the function. We just know that a vector and a matrix is a very convenient, powerful way of representing sets of numbers. And that's fundamentally the point here, is that that's all it's really doing, is it's taking in a set of numbers, producing some function on it. When those sets of numbers can be represented like this, where the function is a linear function, there are some nice cases where the derivative collapses back onto just being the transformation itself. It's the closest linear approximation to a general function. That was the point of the kind of last thing we did. However, the main important thing of why we have a matrix here is so that we can do the summation with it. That is the key bit. The reason we want to do the summation with it is that we can sum up all those little changes to ultimately decide on what's happening to f. Okay, so you can think of it in terms of the example. Let's say that. So I have f here as being m dimensions. So let's say this is 2. I have two things I care about: my bank balance and the amount of crypto I own. Okay, so I'm optimizing two output functions. That is a function of n input variables, and we can call that 3 different input variables, right? Now, those 3 variables will be, again, my salary, the amount of time that I've been investing, and what's something else that matters? The current interest rate. I have 3 input variables. They are mapped to the 2 output values by A, right? A being bank account crypto. So there is some function that says, given the state of how much money I'm earning, how much time I've been investing, what's the interest rate, that can give you the answer of what my current portfolio is of bank account to crypto, right? What I then want to know is, when the interest rate rises, how does that affect my portfolio? By this function. Okay, and so I'm going to take the derivative. I'm going to say, well, what's the derivative of f with respect to x2 or x3? It was the third variable. You hear what I'm saying? Okay, well, to do that, you're then going to have to say, well, okay, those are sitting in different matrices, right? So this is the, and let's say we're focusing specifically on my bank account. We're not going to worry about crypto. Crypto doesn't factor into interest rate. So I only have to care about F1 with respect to X3. Okay, and that combination, that is now a one-dimensional function with respect to a one-dimensional input, two very tangible things, right? And that's the normal derivative, which I'm sure you're comfortable with. The only thing now is to say, well, I kind of want to sort these derivatives in an appropriate way so that I can also operate on them efficiently. That's a matrix, okay? Because at some points, I'm also going to care about my salary going up. So at some point, the interest rate will rise and my salary is going to go up. So now I need to care about the derivative of F1 with respect to X1 and X3, okay? So we're going to do that, and we're going to work on those instead. Now I have both. How do you stack them? How do you organize them? You make a vector. Why do you make a vector? Well, so that when it comes time to go d of f1, d of x1, d of f1, d of x2, d of f1, d of x3, those are the derivatives. I can then say, well, how much did x1 change? How much did x2 change? How much did x3 change? And we end up doing this 1 by 3 times a 3 by 1 vector, right? So all of these little pieces, they had independent meaning. Okay, that was bank account relative to, what was it, my salary. Bank account relative to salary, bank account relative to time, bank account relative to interest rate. This is telling you how much my salary changed. This is how much time has changed. And this is how much the interest rate is going up. I don't really want to know about all those 3 different systems. What I really want to know is how on earth my bank account's going to change. What is the change to F1? We just add all those little things together, man. Summation over I from 1 to 3, F1, derivative of F1, derivative of xi times y, the change in xi. And you can trust, and again, maths in many cases about, like we think about it once. We structure the system once. Very clever people do it once. And then we just kind of trust that we use the machinery after that. So we've proven it to ourselves that each of those individual elements in the vector and the matrix means something. In this case, right? We've proven to ourselves that we can use it with the summation to add up all of the little effects on F1. We can add them all up and get something interpretable about what is going to summarize as a summary what will happen to my system, to my F1. The dimensions don't matter. You can trust that the matrix multiplication works out. And what I'm telling you is the only way that it works out is when we get our orderings correct. When we adhere to this rule that we structure our derivatives as, I think it went too far. We structure our derivatives as the dimension of the output with respect to the dimension of our input. Then you can come and do as many tensor multiplications as you want. I'll give you a GPU. Go mine crypto with it. You know what I mean? Like, do what you want there. The math works. Does that help you?
Yes, I think it does. Can I confirm that?
Yes.
I want to make sure I understand.
Yeah.
So what you're saying is we know that derivatives are making to us, right?
Mm-hmm.
And then we package them in this thing as we call it a tensor. And
Sorry, we package them in
this thing as we call it a tensor.
Yes. Well, I mean, if it's a vector matrix, then a tensor, but yes.
Okay. So we put them in this. Should I call it a list in this way?
An array is fine.
Okay. We put them there because we know that in a computer it would be easy to encode this.
Yes. Fundamentally, yeah. We know that we can do matrix multiplication on it. We know that matrix multiplication has a summation, which will then just add up all of our little changes. Cool. All right. I do hope that was helpful, and thank you for kind of asking the question. All right. So let's get back to the example. Let's clean this up. Okay, so ultimately we're now in a case, again, we have f outputs. So f variables that I already care about tracking have a times x as our function mapping. And in this case, I want to know how f changes with respect to all of my a's. Okay. Previously in this other example, we were considering how it changes when I change all my n input variables. Now I have this matrix of inputs A. And I want to know how my f's change when I tweak each element of A individually. Okay, that will be stacked as a m by m by m matrix, again, because for every f, I went through all of the elements, all of the rows of A, and I went through all of the columns of A, and at every single element, I did the derivative, which gave me a scalar at that point. I then just package it in a matrix so that it's easy for me to use when I do matrix multiplication. Okay, but the way to solve this and the way to think about this is to consider these things in isolation. So I don't really like thinking about tensors. Tensors are hard. What I would much prefer is to think about a matrix. And so instead of thinking about all of the f's, I'm just going to think about one of them, fi. Call it I so that it's general. I don't actually care which f. I just want to know that when the time comes, I can think about it. So fi with respect to all of my a's. Now fi is a one-dimensional output, but my a's are still a matrix, m by n. Okay? But this at least means that I can make a little bit of progress because I can write the output of fi as that matrix multiplication, right? That's the summation version of matrix multiplication. We've seen it throughout. Okay, so at least maybe now I can come through and start doing a derivative with respect to this. Maybe that helps me a little bit. And so this is ultimately the steps that you're always going to follow when you're doing these derivatives. First, you say, what is the dimension? Okay, then you're going to try and write the output in terms of the underlying summation and the underlying function. All right, so for every input f, you're going to write it in terms of all of the input elements a or x. Okay, and then you can come through and you can say, well, I'm now considering essentially, as we did in that example, when I was telling you about my bank account relative to interest rates, you are now going to take that derivative every time. Okay, and so you come through and you say, well, partial derivative with respect to aiq of the sum j equals 1 to n aij xj. You can see that it's now getting tricky. And I agree that these are tricky. You need to be really careful about them. Okay? But what matters, and we saw this in that earlier example, is the fact that this sum over j is going to be going through all of the indices from 1 to n. Only one of those indices is q. So only one point in this summation am I going to have a I q x q. And only in that point, when I do that partial derivative with respect to aiq, does that now fall away, right? We know that that's the derivative rule. That's a one-dimensional thing. And so we end up with xq. Okay? What is the other case? Well, all the other elements of that summation, it's not q. It's going to be hard. All of the other elements of the summation, we now have all elements of j going from 0 up to n. There is no aiq in any of those elements, and so they all map to 0. And so as a result, we know that the derivative of fi with respect to aiq is xq. All right? Is that somewhat comfy? Making sense? And as a result, what does that mean? Well, it means that only when I have this q, this index going over the columns, yes.
Why does the aiq in, I guess, the previous thing fall away when you do the partial derivative?
The derivative of, so you have a times x. the derivative with respect to x is a. Okay. All right. And so now it's just a case of considering again these shapes, right? And so in this case, we had a one-dimensional function. We were considering only the ith row of A, and we were then varying Q. Okay? And so we have a 1 by 1 by n. And that's the way you need to reason about it. That's how you know how to package them back. We were iterating over the last index of our inputs. And so the thing we affect, the thing we're currently building, is that last index of our derivative. You will then come through and you will stack them again. But you consider all the elements of your system in isolation. That's why it's a partial derivative. Right? Yes.
Is xj a row vector?
Xj is column. Yes. This is f is equal to ax. Stop. Do I need to write out the matrix multiplication again or explain that? We're good. Okay. Okay. There is one alternative to this. The one thing we haven't done yet is considering, well, what happens if this I does not match the fi? Well, in that case, there's no chance of me getting aij in the appropriate place, and so it's 0. So there is only one index that works. It's aiq, where I is matching the output dimension we are considering, and it's connecting to the input dimension we're considering. This is the value that says, how does interest rate affect my bank account? And only that value, because that's the only one that connects bank account to interest rate. Okay. You'll then come through and stack them. So for every output, you know that they're going to be 0, except for the one that was fi. And that is the ith row there. Okay? All others are going to be 0. And then after that, you will just stack all of these together so that you get into your fi cases. And that'll look like this. You stack them in terms of the height. But again, you knew it was the height because you're going to stack them in that first axis. So with respect to every function fi, I have now taken the derivative with respect to every input in my matrix A. That's a 1 by m. And so I know that I don't just have one function, I have multiple of them, so I stack them. And that is just a convenient way of representing this, because then I know that it's in a matrix and I can do matrix multiplication and I can do a whole bunch of other clever operations on it. Ultimately, and maybe this also serves your, helps you, ultimately the reason that matters is because it's the closest linear approximation to the actual function. That is also why a matrix is useful, right? We showed you that in this example of the Jacobian earlier. And again, that is, I know I get excited about it. That is a subtle thing to appreciate. The fact that this is taking you as close to imitating a nonlinear function as you can with a linear mapping. That is the thing that connects linear algebra to calculus, is the derivative, it's the Jacobian. It's only valid in that area where you did that derivative. But that is really, really useful. And that is then also why matrices help. It's that consistency between those two systems. Okay. We have half an hour left, and we have this one example to go through, and I'm happy to go through it slowly as we need. So consider now one last case. We have R. We have R, which is an m by n matrix, and F, which is an m by n matrix, and this maps to an n by n. We actually don't need F, so that can also just be R. And that's fine. In this case, the function we are computing is we're taking R, we're transposing it, and then multiplying with R again, and we're going to call that K. All right? Ignore all the fluff around the other notation. F is now that function mapping. But anyway, so can you find the derivative that takes me from K and tells me how that is affected by R? Okay. So 2 bits of information we have. K is an n by n matrix. It is the output. R is my input. It's n by n. What will be the dimension of the derivative? Dimensions of the derivative. Correct. There we go. All comfortable with that? It was the size of the output by the size of the input. And you just copy it across. Almost no need to think. It is a mechanism that you can just know of. So there we go. N by n by m by n. We're going to take every element of that output, n by n, and we're going to take the derivative with respect to every m by n input. This gives you a 4-dimensional or a 4th order tensor. Cool. And so we can consider then the components of, quote, the first matrix. All right. Because it's a 4th order tensor, it is essentially a 2D matrix of 2D matrices. All right. So we can consider, well, what is just one of those matrices? What is just one element of K? How does that respond to the derivative with respect to all of R? Okay, that's the first thing we can maybe consider. But we can actually get even better with this and break it down completely into how every single element of our system interacts. And that is what we're going to do now. There's a, I see. That is what we're going to do now. Okay, and that is the way you approach these problems. And so you've now said what you know the output to be, and you know it's correct. You don't have to think about that anymore, but that will help you structure it when you have to put these things back together. We know how to combine the numbers back into our matrix. So now what we're going to do is just figure out how to get the numbers, and you can put the two things together. How do you get the numbers? Well, you write out each element of the output in terms of the input. So PQ. It's a 2D output. We told you it was in n by n. So those are all indices of this n by n matrix. Okay. That is going to be written as the pth row, or sorry, the pth column of R times by the qth row. All right. This is just the matrix multiplication. What we've done is written out this, but only considered the appropriate row and column that needs to be multiplied to get the value. Okay. The last thing to note, then, so this corresponds to RP up there, and then this is RQ. If you want to just use the subscript of the original matrix, they did the little r anyway, just to keep it clear that this is now a vector. That's why they're using the little r there, but you can use the big R if that's better for you. Now, one thing that's important to note is that this is transposed, and so what they're ultimately going to do is flip those two indices. Okay. R transposed, we're looking at P and M, and then times by R, M and Q. When we do the matrix multiplication, we know we sum over M, and what we're left with is the output is the dimensionals on the output, the indices in the output. Okay, so P and Q there. The only thing they're doing is, instead of writing transpose and keeping the internal elements M, they've now just swapped them and dropped the transposed. Reason being is that becomes a little bit easier to now think about the different cases that we're going to deal with in terms of R. Okay, so you can see here R is the ith column of R. So now you can compute all elements of the derivative of K with respect to R just by considering this pairing. Okay, we know how, again, at the top here, when we decided that it was the appropriate dimension, we know how to structure these constructs. We now just need to know, how do I get a single value out of it? And there are going to be a few cases to the different kinds of values that might come up in the matrix. And those are things we have to do now. You're going to consider the different conditions. But you go through them one at a time. So firstly, what we're going to do is we're going to say, well, okay, here's KPQ. I know how to write that in terms of the matrix multiplication, right? At least that was kind of okay for me. So I'm going to copy that in there. All right. So now I know that I have the summation, which should have been on the out, well, could be on the outside. Rij there. Second step, I know that we can do the linearity of the multiplication, right? I know that I can, the derivative of the sum is the same as the sum of the derivative. So maybe it's helpful if I pull it in and then just consider these pieces here for the moment. Okay, so that's the important bit there. Now we don't even have to think about the summation. First, all we're doing is considering how this derivative plays out. We've abstracted away matrix multiplication, summation, the different ways that we stack into the fourth dimension of the tensor. And all I have to do now is consider this one derivative of a scalar value or two scalar values, which is that. Okay, now this is where we play our usual trick from before, where we now try and say, well, where are there going to be zeros? So to begin with, let's say that, and this is, I need to make sure I'm careful. Let's say that we're in a case where I is not summing over M. M is going to go in there. Let's say we're in a case where J is not equal to either P or Q. Okay, so those are two different variables. Is there any chance of us getting a match on that derivative for any value of M? So regardless of what I'm doing with M there, is it possible for this derivative to work out to anything other than 0 if J is not equal to P or Q? No, right? So you get the 0 otherwise. I think that's the easiest place to start. Just look for the 0 case. The indice that you are not summing over has to match one of those two things. If not, doesn't work. And then you come and you say, okay, fine, that helps. What happens if J is equal to P? But maybe P and Q are different. Okay, well, then we're going to come and we're going to do the summation, right? So now what we're doing, we've assumed that J is equal to P. So what we're actually evaluating is M is equal to 1 up to M, derivative of R I P, and you have R M P R M Q. Okay, so you've substituted in that assumption. J is equal to P. That's static now. We know that. Okay, the summation is now happening on these M variables. And actually, there is one case where this derivative will work. And it's the case where M is equal to I. Because in that case now, we end up doing the derivative of RIP with respect to RIP RIQ. That falls away. What are we left with? RIQ, RIQ. All other elements of that summation are 0. They fall away. We don't have to think about them. The same pattern holds the other way around, and we can do it again just out of completeness and out of comfort. Okay, so we're going to come through and we're going to say, well, I'm going to make another case. What happens when J is equal to Q, but Q and P are not equal? So now we're going to have summation M is equal to 1 to capital M. J is equal to Q. R MP or MQ. All right, looking good. There's a possibility in that summation for a match with the Q's. But now we're going to consider the summations. The sum is going from M is from 1 to capital M, and in that range, in that summation, there's that one case where M is now equal to I. There's only one, and in that case, you will now have the derivative of RIQ, RIP, RIQ. And so once again, you now have a hit. That falls away. What is left is RIP. In every other case, it evaluated to 0 in that summation. Okay? And then lastly, there is the one case now that we do have to consider, which is what happens when P and Q are also the same. Okay? So now we say, well, come on. Last case, J is equal to P and Q. Okay, well, let's play it out. M is equal to 1, going to capital M, derivative of R, I, P, and it's operating on R, M, P, R, M, and Q by assumption now is equal to P, so we've got P again. So in reality, that is now actually RMP squared. All right? We take that derivative. Does anyone want to tell me the index where we get a hit? What value of M works in this case? I think I heard it, yeah? Correct, there we go. Let's consider the case of M equal to I. All right, I mean, so we have the derivative of R, IP, R, IP squared. What does that give you? 2 R, IP. They chose Q, I chose P. By assumption, they're the same value. And we've now done all 4 cases. I can tell you exactly the dimensions of my system, and I can tell you exactly the 4 different kinds of variables you will get in that matrix. And so I've solved the derivative. That's sufficient. That's done. If you're in a test, you don't go beyond this. No one, I don't want to see you try and write a 40 tensor on paper. If you can, you deserve a lot of money. But that's it. We just need to know that we just need to know the final dimensions of the matrix. That matters to our system. And we just need to know how each of the values are going to be defined. You've done your derivative. But you need to go through it slowly. You need to consider the cases. All right. And ultimately, what's going to end up happening is your case, you're going to end up with one variable which is being summed over. Okay. And then another one which is going to be taking on the other value. And because in this case we had 2 other indices for R, we got 4 different cases. There are easier versions of that, obviously. But do it step by step. Start by saying, what's my output derivative? Or sorry, dimension. Then start by writing the output function. Just what is that one element of my output function? How do I write it in terms of my inputs? Then you bring that down here and you say, well, okay, I'm going to now just take the derivative with respect to my input and make sure you use different indices, right? Because it's all of your inputs with respect to all of your outputs. There are obviously now different indices. Why do we have to know that there are different indices? Well, because I have to have one indice for the number of dimensions I have output, right? That's n by n by m by n. I need to be able to index into this 40 tensor somehow. And so I have the n, m, n variables, indices. Okay, and so now it's principled. Now it's structured. Now all I have to do is substitute that in and look where my where I might get matches coming out of those indices. Luckily, I'm summing over 1, in which case I don't have to actually consider what I is doing because I know that the summation is going to do all I's for me. I just need to go look for the one case where M happens to be correct. Yeah.
We like setting like these J's in this formula, like, yeah, isn't the index we get the hit for always going to be I?
That's just correct, yes. There's a lot of pattern into it. But yeah, I think doing it from first principles helps. Okay, and there's a lot of these things. This is I don't know if you guys know this. There's a textbook called the Matrix Cookbook. I would recommend you go look it up. Really useful. Helps a lot with your honors research towards the end of the year. But these are a list of rules. So there's a lot of these, right? There are a number of useful grading identities that are frequently required in machine learning. These can be seen as given unless said otherwise. These will be provided in a test-like setting. must be funny. There's very few of these that you even need in my tests. I'm not trying to be pedantic. I do want you guys to be able to do this. There's an example in your tutorial that you should go through. But these are here more for your convenience and more for your kind of interest, I guess. A lot of these get hard to compute. So that's it for today. If there's no other questions, I know that last bit is hard, and I know that feels like it ramps up quickly considering it starts as one by one derivatives, but such is the course. Yeah, something.
When you're considering all of this stuff, does a Jacobian always have to be like linear?
Correct. Correct. Because it's only a matrix.
Just a bit up on the page above. Yeah, so I'm not really sure how we got the RPERQ.
Sorry,
Like the KPQ, like 15. I don't know how that middle piece came about.
Oh, okay. This is matrix multiplication. All right. So we know that K is this.
Yeah.
Okay.
That's just what we defined it as.
Yeah, that's just the function we've been given. And so we can write that as the summation, right? So then Kij is equal to RIM transpose of that transpose matrix, RMJ. That's just the definition of matrix multiplication. It maybe helps if we're not looking at transposes in R's. So for example, if I did this instead, A times B, then Kij is summation over M. Sorry, I've got the summation on the previous example. A, I, M, B, M, J. That is literally just the way of defining matrix multiplication.
See that K was defined by the transpose. I was like wondering where it came from.
Oh, okay. Sorry, my bad. If I went through that too quickly, I'm sorry. Okay. Yeah.
So this is how big
I keep them pretty small, man. I mean, again, I'm more concerned here with the. Well, in fact, that's arbitrary because the only thing I'm going to ask you is size. So, you know, N and MM can be whatever I want them to be. And then after that, you're just going to do the cases. Know what I'm saying? Like it's, you're never, I don't expect you to write out the answer matrix. But the number of cases tends to be manageable, if I can put it that way.
And the subscript indices, like we have KPQ there, that's just arbitrary.
Arbitrary, yeah. Yeah, we'll mark that appropriately. I tend to mark this question in the exam because it's hard. Yep.
Yes, we've got non-linear Jacobians.
There is only a linear Jacobian.
So you couldn't get like take a 2x in one of the indices.
No, yeah. So it's always going to be a matrix. You can get a nonlinear function.
Yes.
Oh, I see. So like, for example, what if we were doing this activation function here, where this is your sigmoid. It's just chain rule. It's just chain rule after that. So in that sense, now what you're going to say is every KPQ is now your sigmoid function, acting element-wise on those items. Right? And so now you're going to first do the derivative of that. RMP, RMQ. Okay. You know, that's just chain rule of one-dimensional systems. And then you end up doing this again. And then you do your cases. And then this is now a constant you pull out the front. This one here. You know what I'm saying? So it obviously depends on, it's like a constant in the sense that like it depends on where you, which indices you're operating on. But, you know, at least then it's, you say that's like the scalar input to the nonlinearity, the nonlinear function. That is now the derivative of that function out front. And then you do your cases like that again. But I can promise you I'm not going to do that. Like that's also just really unnecessary, especially in this class. So the thing I'm going to teach you next week, there's a couple things I'm going to go through next week. Firstly, I'm going to show you, have you guys heard of Einstein notation? Einstein notation is a way of writing summations like this that make it quite easy. So I'll show you Einstein notation. What's cool about Einstein notation is that in NumPy, there is a function called einsum. And I'll show you how einsum works. And it's essentially a general function to do high dimensional tensor products. And it's very useful as a data scientist. It's the kind of thing that admittedly you're probably going to use once a year, but the day you need it, your boss is going to be really impressed when you do that. I need it for a project now, and it's just saved my life. Because writing out matrix multiplication, J and P dot every 2 seconds sucks. But just it's a really nice way of writing out matrix multiplication. So next week we'll go through that, and hopefully that puts into perspective, number one, why kind of coming up with good notation, understanding like einsum in NumPy is useful because it saves you doing all this nonsense. Secondly, we'll then show you automatic differentiation, which also saves you from doing all this nonsense. Now it's a really principled way of going about just doing a lot of the workload. Okay, so obviously you could still pass in matrix functions into automatic differentiation, but at least next week now we've gone through the basic hard calculus stuff. Next week we should see some of the recent advances and the kind of cool ideas that make things more efficient and easy. Cool. Anyway, that's the problem. If no one has any questions, we can wrap up for today. Good. All right. Thank you, guys.